This video will analyze flow characteristics over a cylinder. The experiment included testing flow at 3 different Reynolds numbers, tripping the boundary layer, visualizing vortex shedding frequencies, and analyzing data to find variation in coefficient of pressure and drag force. Cylinders are an important object to analyze because they show up so often in real life. Cylinders are used for bridge pylons, bridge supports, rockets, hang glider frames, planes, and more. Studying the dynamics of flow around cylindrical shapes is crucial to avoid structural failure for all of these real-life applications. The separation point of these objects can be controlled with tripwires, circular wires, or sandpaper or rough materials.
Forces acting on any object will consist of pressure and wall shear forces that act normal and parallel to the direction of flow. Pressure forces parallel to the flow direction are known as drag forces, which is what this lab will observe and quantify using pressure ports on the circumference of the cylinder. A cylinder is the ideal shape for this experiment because flow will only move over and under the surface, rather than around all sides like it would for a sphere. A cylinder has more aerodynamic shape than a cube or rectangle, so the shape won't be the main cause of turbulence, but it has an easier shape to trip the boundary layer on than an airfoil. A cylinder should clearly show where the flow separates and how Reynolds numbers will affect the flow regimes. The lab also observes the effect of tripping the boundary layer, which is achieved by placing some kind of obstruction at the location of flow separation. Sandpaper, grip tape, tripwire, and much more can all be used to obstruct flow, trip the boundary layer, and cause turbulence. Turbulence will cause a reduction in pressure drag, which delays the boundary layer separating. Flow separation occurs when the speed of the boundary layer over an object slows to almost zero, and the flow becomes detached from the surface. Separation increases pressure drag, so engineers must make design changes to minimize drag such as dimples on golf balls or turbulators on airfoils.
Before the lab began, a smooth cylindrical tube with an 11.43 centimeter diameter had 24 evenly spaced static pressure points installed and was secured in the wind tunnel. The tasks involved in this lab included operating the smoke machine, recording footage of the flow around the cylinder, positioning the laser and lights above the wind tunnel, collecting data from LabVIEW, running the data through MATLAB, and operating the wind tunnel. Before turning on the wind tunnel, the safe working procedures were reviewed, the cylinder's position was double-checked, the fog machine was set up, and the overhead laser and lights were turned on. Pressure data was collected with the wind tunnel off, and then twice at 1 meters per second, 16 meters per second, and 25 meters per second. The separation point was noted and estimated at 45 degrees from the stagnation point. The wind tunnel was turned off, and 2 tripwires were placed along the cylinder at 45 degrees above and below the stagnation point. Pressure data was collected 2 times each at 1 meters per second, 16 meters per second, and 25 meters per second to see the effects of the tripwire. After the test was complete, the wind tunnel was safely turned off, the cylinder was carefully removed from the test section, and the lab was tidied up. Static pressure readings are difficult to make because disturbance of the pressure ports can alter the results, and they should be parallel to the flow direction instead of at varying angles. This lab assumed the flow was only 2-dimensional, but this assumption is not realistic since the air being pulled into the test section is from various angles and directions. Flow in the third direction could also alter the results for lift and drag forces. Flow velocities of 1 meters per second, 16 meters per second, and 25 meters per second resulted in Reynolds numbers of 1.2 times 10 to the 5th, 2.4 times 10 to the 6th, and 3.7 times 10 to the 6th, respectively. At 1 meter per second, the flow is laminar. At 16 meters per second, the flow can be considered transitional or turbulent, depending on your beliefs, and at 25 meters per second, the flow is fully turbulent. These values were found by Reynolds number equals density times velocity times characteristic length divided by viscosity. The theoretical boundary layer thickness for no trip flow over the cylinder were 1.43 centimeters for 1 meters per second. 16 meters per second has transitional flow, so the thickness of 1.79 centimeters was found by interpolating the laminar and turbulent thicknesses. For 25 meters per second, the thickness is 1.84 centimeters. Laminar thickness is found by 4.91 divided by the square root of Reynolds number, and turbulent thickness is found 0.16 divided by Reynolds number to the 1/7. These thicknesses are for the start of the cylinder. The boundary layer thickness will increase as the flow passes over the cylinder from 0 to 180 degrees.
Mapping the cross-section of a cylinder onto Cartesian coordinates yields a sinusoidal wave. In a perfect flow without separation, a Cartesian plot of pressure around the cylinder should be a perfect sinusoidal wave as well. However, fluctuations arise due to viscous effects along the surface of the cylinder, the most drastic of which being separation. When separation occurs, turbulence is introduced, which actually appears to be somewhat constant to the pressure ports due to the chaotic and multidirectional properties of turbulence. This means that the pressure plot around the cylinder will detach from the sinusoidal wave, remain constant throughout the wake region, and then rejoin the sinusoidal wave at the location of separation on the bottom surface. The closer the plot matches the sinusoidal wave, the better. In theory, the lower the separation from the sinusoid occurs, the less drag there is. When running the wind tunnel around 1 meter per second, it is clear that the flow has a lot of time to fluctuate. Adding a trip strip to the cylinder doesn't seem to change the angle at which separation occurs, nor does it have much effect on drag. In fact, by tripping the flow, a higher pressure coefficient was created on the backside of the cylinder, causing more drag. Overall, the low speed plus a few large bumps in the wake on the tripped plot result in minor changes. Increasing the airspeed to about 15 meters per second yields some nicer looking graphs. Here the separation angles are clearly defined and there is a huge difference in drag. Notice that when the flow is tripped, the pressure plot follows the sinusoid much better than when the flow is not tripped. It appears that following the sinusoid has more influence on drag than simply being a lower value of Cp. Here, the drag force decreases by nearly 30%. Increasing the airspeed still yields similar results. At 25 meters per second, there are two clear separation points, and the tripped plot follows the sinusoid better than the non-tripped plot. As learned from the previous slide, we'd expect drag to decrease significantly because of this, and sure enough, it decreases about 20%. Without a trip strip, the three airspeeds are shown. 1 meters per second has the most separation, followed by 25 meters per second, then 15 meters per second. It seems that high speeds may be slightly less efficient than medium speeds. A more helpful graph would be one that shows the deviation from the sinusoid. This shows the deviation from the theoretical value for each speed. Notice that 25 meters per second is on average the closest fit to the theoretical value at about 60%. However, all three speeds are relatively similar with no huge difference in deviation. Now, a trip strip has been added, and right away it is clear that there is some improvement. 1 meters per second has lowered, and the two faster speeds follow the sinusoid a bit better. Another deviation graph would quantify these values. Comparing the no-trip deviation graph to this graph shows that all three speeds improved when adding a trip strip. Notice that 15 meters per second improved the best, decreasing its deviation by 8%. Overall, it appears that a speed range emerges in which flow is most efficient around a cylinder, not too slow but not too fast. To better define this range, more tests would have to be conducted. However, this claim can be supported by the drag calculations for each speed. What is panel code? Panel code is a method for estimating some property of an entire object by summing up the properties of small portions of that object. In this case, a panel method will be implemented such that the total drag will be found from summing up the drag forces created on 24 pieces or panels of the cylinder's surface. Each panel has an associated pressure that points normal and inward to the panel's surface. This value is used to calculate the coefficient of pressure. Using the coefficient of pressure, drag on that panel can then be calculated. It is important to only consider pressure in the direction of flow as per the definition of drag. This means the angle at which the panel lies in the free stream must be taken into account. In the case of the cylinder, the pressure values on the back side turned out to be negative, but remember that that assumes an inward normal vector. Therefore, positive drag should occur. Panel method is simply an experimental way to approximate a value that could be found mathematically using an integral. Using the panel method, drag values at 1 meters per second without tripping the flow is about 1 Newton. Increasing the speed to 15 meters per second yields a drag of about 216 newtons. Up to 25 meters per second yields a drag of about 450 newtons. These numbers are interesting, however it would be better to see how drag responds when removing the influence of velocity. For 1 meters per second, drag divided by velocity squared is about 0.54, 15 meters per second is about 0.86, and 25 meters per second is about 0.75. This means that without a trip strip, medium speeds are actually worse for drag. Adding a trip strip yields drag values of 1 newton, 154 newtons, and 357 newtons, respectively. Dividing out the velocity influence again yields 0.84, 0.58, and 0.57 for the same speeds. This shows that at low speeds, adding a trip strip makes the flow worse. But for high speeds, a trip strip decreases drag. This supports the findings in the previous deviation calculations. These results are expected. At 1 meters per second, the flow was laminar all the way through, so adding a trip strip actually created more frictional drag than it was able to reduce in vortex drag, also called induced drag. However, once the flow was increased to transitional or turbulent, adding the trip strip reduced more induced drag than it caused in frictional drag.
This experiment showed tripping the boundary layer has more effect at higher Reynolds numbers. Higher Reynolds numbers naturally have less separation, and tripping the boundary layer using a tripwire at roughly 45 degrees from the stagnation point for higher Reynolds numbers did allow for less separation and less drag.